Hello friends, so here is another question on full wave rectifier. So the question is that the four diodes used in the bridge rectifier circuit here, they have forward resistance of 1 ohm, the alternating secondary voltage, secondary voltage is 240 volt RMS and the load resistance is 480 ohm. Calculate the mean load current and the power dissipated in each diode. Okay, this. So now here for a bridge type rectifier circuit, you see that at any given instant only two diodes are conducting and two of them are open circuited or off. Okay, so if we take it here, so at any given point of time, if we consider, let's say, the positive half cycle, okay, if we consider the positive half cycle, let's say this is the positive half cycle. So in this case, this diode, okay, this diode where the positive, here this is the negative, the positive is connected to the P and the negative is connected to the N. This will conduct and it will, we can replace it with its forward resistance, okay, we can replace it with its forward resistance, okay, that is RF, okay, RF is equal to 1 ohm, and this diode, okay, where the negative is connected to this, okay, this diode, this will also conduct and we can replace it with its forward resistance, okay, this. RF is equal to 1 ohm, okay, and to simplify the circuit, these two can be removed totally because they are open circuited. Plus end is connected to here, in this case the plus end is connected to the N negative and here the minus is connected to the P type end. So these two diodes will be open circuited. These two diodes will be open circuited, okay, and we can connect this load resistance here, the same thing it is. If we connect the load resistance in this way also, it is the same thing, 480 ohm, it is the same thing. So here this is the RMS value, which is 240 volt RMS, the secondary winding voltage. So the maximum value of the secondary winding voltage is equal to 240 into root 2, okay, the maximum value. Now, so we have been asked to find the mean load current. So for that we have to determine first the maximum load current, okay, the maximum load current IL max is equal to Vs max by here 2 RF plus RL, the total resistance, twice forward resistance, two diodes are conducting, so 2 RF plus RL, which is equal to 240 root 2 divided by 2 into 1 plus 480, that is equal to, it is coming around 0.7 ampere, okay, and we know that the DC value of the current is equal to, for full wave rectifiers, it is 2 I max by pi. So in this case it will be 2 IL max by pi is equal to 2 into 0.7 by pi, 3.14. So it will come around is coming around 0.45 ampere. Okay, then it has been asked to find the power dissipated in each diode. Okay, here please pay some attention. Here the rectifier circuit, it conducts during both positive and negative half cycle. That is, during the positive half cycle these two diodes conduct, okay, these two diodes, this one and this one. During the negative half cycle these two diodes conduct. But if we consider a single diode, okay, a single diode, then one diode conducts only during one half cycle. Okay, pair of diodes conduct in each half cycle. In each half cycle they conduct. That is, one diode conducts in each half cycle. Okay, one diode conducts in each half cycle, whether it is positive or negative. So here, to determine the power dissipated in each diode, we have to determine the RMS value of the diode current, which is similar to half wave rectifier, because in half wave rectifier diode conducts only during one half cycle. Okay, conducts only during one half cycle. It can be positive or negative. Here also the situation is same. See, understand the difference. Here it has not been asked to determine the power dissipated during the entire. Here during throughout the load resistance, then the situation would have been different, because current is always conducting through the load resistance during both positive and negative half cycle. In that case it would have been different. Here it has been asked to find the power dissipated in each diode. Now here, as I said, only a pair of diodes conduct during one half cycle. So it means one diode out of the four diodes, it conducts only during one half cycle. So in order to determine the power dissipated, we have to determine the diode RMS current, which is similar to half wave rectifier, which will be the maximum current divided by 2. Okay, the maximum current flowing through the diode divided by 2, which is same as IL max by 2, because the same load current flows through the diode, which is equal to how much? 0.7 by 2, which is equal to 0.35 ampere. So the power dissipated in each diode, the power dissipated in the diode is equal to diode RMS current square multiplied with the diode forward resistance, which is equal to 0.35 whole square into RF, which is equal to 1 ohm, that is equal to how much? 0.123 watts. That is the power dissipated in each diode. So here, for this bridge type rectifier circuits, we have been asked to find the mean load current, which we determined here, that is the DC value of load current. That is the same, mean value, DC value, average value, it is the same. Then we have to determine the power dissipated. For that we determine the RMS value of the diode current, and then we determine the power dissipated in the diode. This. Okay, so here you have to understand, it is not the power dissipated through the load resistance. Here it is the power dissipated in each diode. That's why we used this formula, the RMS formula, which is similar to that of the half wave rectifier. Here you don't write it is ID max by √2, then it will be wrong, because we are considering only one diode, not the entire bridge rectifier circuit. Okay, so this is the solution. Hello friends, so here is another question. So here it is given that the bridge rectifier circuit, which is given here, it uses silicon diodes with cut-in voltage 0.7 volt, and the remaining data is given here. okay, we have to find the DC output voltage and the DC output current. Okay, so here there is no mention about the supply voltage, no mention about the turns ratio. Directly it has been given that the RMS value of the secondary winding voltage is 12 volt. Okay, that. So first we will copy the circuit. Okay, okay, here. So here the RMS value of the secondary winding voltage is 12 volt. Okay, from here to here. So now the maximum value of the secondary winding voltage, which will be the maximum value for the rectifier circuit, as it is a bridge type rectifier, it is 12 into root 2, which is equal to 16.97 volts. Okay, this. Another interesting thing in this question, it has been mentioned specifically that it is a silicon diodes with cut-in voltage 0.7 volt. No information has been given about the forward resistance, so we'll assume it to be 0. So we'll assume that it has a built-in value, okay, the cut-in voltage value, which is equal to 0.7 volt, and the forward resistance is 0. So here when a diode is conducting, we will replace it like this. Okay, this cut-in voltage 0.7 volt and no resistance, no forward resistance. Again, you know, in a bridge type rectifier circuit, at any given point of time, only two pair of diodes, opposite diodes, are conducting. Remaining two diodes are off, open circuited. Okay, during non-conducting state, the diodes will be replaced with open circuit. Okay, this. During on state, it is replaced with the cut-in voltage 0.7 volt. So here if we consider the positive half cycle, the same situation will be during the negative half cycle. Let us consider only the positive half cycle. During the positive half cycle, this is plus, this is minus. Plus is connected to here, the P end of D3, minus is connected to the N end of D3, so this will conduct, D3 will conduct. So we will replace it with a cut-in voltage 0.7 volt. Okay, this, like this, 0.7 volt. Similarly, minus is connected to the N end of D1, plus is connected to the P end of D1, so this will also conduct, D1 will conduct. Again, we'll replace it with its cut-in voltage. Okay, like this. .7 voltage, 0.7 volt. Now D2 and D4, plus is connected to N end, minus is connected to P end. So this will be off, it will be open circuited. And D4, minus is connected to P, plus is connected to N, this will also be open circuited. So this will be the circuit. Okay, this will be the circuit like this. This is V secondary max, which is equal to 16.97 volt. Okay, it will be like this, the current will flow like this, and the voltage will appear in this way. The output voltage will appear across the load resistance in this way. Okay, the current will flow like this, like this, like this, then like this, then back like this. Okay, the diode current or the circuit current. Now here the output voltage will appear across the 12 kilo ohm load resistance like this. So here maximum output will be obtained when the current flowing is maximum. Okay, that. So here, and that will occur when the secondary winding voltage is maximum, which is 16.97 volt, V max. So V out max, if we apply KVL here, V out max is equal to, if we apply KVL, 16.97 minus 0.7 minus V out. So here already we have taken the V out, so here no need to do that, minus 0.7 again, this 0.7, and that is equal to, it is coming around 16.97 by 1.4, which is 15.57 volt. That is the maximum value of the output voltage. Okay, now the DC value of the output voltage, it is equal to 2 V max by pi, that is 2 V out max by pi, which is equal to 2 into 15.57 divided by pi. So that is coming around 9.91 volt. Always remember these formulas. The DC value is 2 V max by pi. Okay, 2 V max by pi. For full wave rectifier, RMS value is V max by root 2. Okay, for full wave rectifier. For half wave, it is simply V max by pi or I max by pi, and it is I max by 2, V max by 2, the RMS value. These formulas are very important, you should remember. Then we have determined the DC value of the output voltage, then the DC value of the output current is simply V out DC by RL, which is equal to 9.91 volt by 12 kilo ohm, which is equal to, it is coming 0.00825. So if we want to express it, we can write it as, okay, we can write it as 825.8 microampere. This, okay, this 9.91 divided by, yes, 825.8, this one microampere. This is the DC value of the output current. Okay, so very simple question, but very conceptual. Here the cut-in voltage concept came into play. It was mentioned that it is silicon diodes with cut-in voltage 0.7 volt. So it means if the diode is on, it has to be replaced with its cut-in voltage. If it is off, it has to be replaced with open circuit. So we took the case of the positive half cycle, where D1 and D3 are conducting, opposite pair are conducting, D2 and D4 are open circuited. We applied KVL in this closed loop. We found out the output voltage, the maximum value. Then from that we determined the DC value of the output, and then from that we determined the DC value of the current. Okay, so this is the solution.